Hello, PreCalc. Today we're going to talk about Edgenuity Section 10.2 called Limits and Continuity. We've got four objectives for this. They are to use limits to determine if a function is continuous at a point, determine the types of discontinuity of a function, describe the behavior of a function around discontinuities, and to apply the extreme value theorem. So this goes a lot with 10.1, where we saw a lot of discontinuities. We saw those jump discontinuities. We're going to see things like that. We're going to see holes. We're going to see all sorts of stuff. So let's take a look at our first problem. All right. So this one says, using limits for which value of x is the function continuous, and we want to choose all that apply. So we're going to say that functions are continuous at any value, and we've got choices of values here. Essentially, we have to test each of these values for continuity, right? And there's going to be one that's weird, and that's where I'll kind of focus our conversation. But the idea is that nothing weird happens at the limit there. And that is what we're going to focus on, is the limit. So, for instance, at -2, we're right here, and you'll see that nothing really weird goes on at -2. -2, as you approach from the left and right, same thing. We do have this other discontinuity point here, and this is you can tell it's a jump discontinuity because it jumps afterwards. And so that's how I know that -1 is not continuous. Because at -1, not only do we have a jump discontinuity, but as I approach from the left and from the right, those one-sided limits are different. And that is how I know that it is not continuous at that point. At 0, we're right here at 0. There's nothing weird going on at 0, so that one's perfectly fine. And then we get 3. And we've got a jump discontinuity at 3. But notice that as I approach from the left and as I approach from the right, that those values those limits would be the same. That limit would exist and it would be one value. And that's sort of a special type of continuity there. That limit exists, but it's still a discontinuity there, right? So is it continuous right exactly at x equals 3? The limit exists, but is it continuous? Well, not really. And then at 5, there's nothing weird going on, so at 5, we're just fine. Okay? So, this one's a little bit, D is a little bit ambiguous. Since the limit exists, you might be tempted to say that it's continuous at that point. It's not continuous right at that point, but it is close because the limit exists, right? So there's some ambiguity, or it seems like there's some ambiguity there, but the fact that there's an actual point to it tells me that it's not continuous, okay? That there is discontinuity. I'll give you a moment to look at that. And let's go on to our next problem. Complete the sentences to describe any points of discontinuity in the function. Okay, so now we're being given just equations, functions, and we've got a piecewise function here, an f of x, where certain expressions are describing certain parts of it. And we've got something weird going on at 9. So you might go to Desmos and graph this to get a look, but really what we want to think about are what's going on, for example, this part right here. What x value gives me a denominator of 0? That's going to be important there, right? And it might be worth going into Desmos and putting this in, and you'd have to put in as two separate things and then look at them near that 9 value and ignore them in other places. And I'll give you a sketch of what this looks like. And this is really the intent of this problem, is for you to do this. So we may as well do it. But keep in mind that what we really want to think about is when that denominator is 0. Okay? And when the x value is 9, we want to think about that too, but we'll think about that as we go. Okay? So if you look at it in Desmos, it kind of looks like, let me just make a rough sketch here. We've got at 3, notice that if x equals 3 for this, it's going to be 0 over 0. So there's something really weird going on. Or no, not 0, I'm sorry. Not 0 over 0. It's going to be 27 plus 27, 54 over 0, 9 minus 9. And when we have just a denominator of 0, that tells us that we are going to have an asymptote, a vertical asymptote. There's some other explorations, and it might be worth discussing them here, actually. Before I talk about the graph, let's talk instead. If I do x cubed plus 0x squared plus 0x plus 27 divided by x plus 3. And we're going to talk about why I did x plus 3, because 3 is the cube root of 27. Okay? So imagine that I do this long division problem, which isn't that difficult. It's x squared there, that gives you x cubed plus 3x squared. Change the sign so that you're subtracting. Those cancel. You get negative 3x squared. Bring down the plus 0x, put a plus, start the game over, and now I need negative 3x. So that's negative 3x squared plus negative 9x. Change the sign, so I'm subtracting. Gives me 9x plus 27, so plus 9, and that'll come out. So then I've got x squared minus 3x plus 9. So again, let's forget about the graph just for a moment here and focus on the algebra, because the algebra is a little more difficult. The graph we could look at in Desmos, right? So what this says is I've got x plus 3 times x squared minus 3x plus 9 over x squared minus 9, which is a difference of squares that I can turn into x plus 3 times x minus 3, right? And notice that the x squared minus 3x plus 9 is not going to factor real nice, so we're not going to bother trying, because, well, you can look at it and say, can I factor it? And you should pretty quickly come to the conclusion that you cannot factor it. So notice that we get a cancellation here, right? And a cancellation is what we call a removable discontinuity, a removable point of discontinuity. So that would happen when these values, when that value is 0, right? So when x is negative 3, we get a removable discontinuity. Okay? What that means is that there's going to be a hole there. Okay? And then I've got this left, and what that tells me is that at 3, I get a vertical asymptote. So there's a hole at x equals negative 3, and there's a vertical asymptote at x equals 3. So the factoring and the canceling or not canceling and denominator being 0 in those ways is what tells me all of that. If I've got two things multiplied right here. If I make this one 0 by letting x equal negative 3, then it doesn't seem to affect anything because it cancels. But it is there. So even though it cancels, I still can't have x equal 3. And that's when we get what we call a removable point of discontinuity, or a hole. Okay? But this one stays, and this one would be 0 when x equals 3, and that's when you get vertical asymptotes, is when you have something in the denominator that makes the entire denominator 0, that is the x value that you put in makes the denominator 0, and it never gets removed, it never gets canceled, and that's how you get a vertical asymptote most of the time. Well, no, all the time. So then that is what we call an infinite discontinuity. So that happens when x equals 3 is when we get that vertical asymptote. And then a jump discontinuity, where we're going to jump values. Okay? So we've determined, let me erase the long division there. It's beautiful, but it's taking up space, unfortunately. And it's served our purposes already. And so let me re-put that we've got a hole at x equals -3. We've got a vertical asymptote at x equals 3. So that's all this. And then let's explore, and by the way, this helps me in sketching it, right? If I wanted to sketch it, I have to know where the hole is, and if I were to graph it in Desmos, I would be able to kind of see that vertical asymptote, but I would not be able to see that hole, right? That hole only is, it's infinitely small. It's only at that tiny, tiny point. And so because of that, it doesn't show up on the graph itself. So having done this math is the only way to understand that that hole exists. And then let's see, okay, so we've got this weird value of 9 here. And so for one part of it, for the top, for this one, if we were putting in 9, we'd do 9 cubed plus 27 over 9 squared minus 9, and that's like some giant number, right? I don't know what 9 cubed is, but it's some really big number. And 9 squared, so this is big. 9 squared is 81, minus 9 would be 72. So it's a really big number over 72, right? So that's still probably a pretty big number, right? If I put in 9 for the bottom, for this, that's 2 times 9 is 18, right? That's not a real big number. I'll do on a calculator what that really big number actually is, and we can talk about the specifics of it. But so 9 cubed is 9 times 9 times 9. That's 729 plus another 27 is 756. So 756 over 72. So if I say that divided by 72 is 10.5. So I get one y value of 10.5. I get another y value of 18. And so that's where we get this so-called jump discontinuity, which is to say that as I approach from the left, as I approach 9 from the left, I'm approaching a value of 10.5, but I'm not actually getting there. So if I was graphing this at 10.5, I would put an open circle at an x value of 9 and a y value of 10.5. And then for this one, I am including that value, so I would put a filled-in circle, a closed circle. And so it would appear that as I move from left to right, I would jump. I would jump up, right? So at an x value of 9, I jump up from 10.5 open circle, immediately jump up to 18 filled in circle, and then continue with that 2x graph. So you can go into Desmos and look at these two graphs and sort of see some of that stuff. if you're looking at the x value of 9, you'll see that they don't intersect, that they're at two different places in that moment. So just something to look at, something to think about at that moment. Okay? So I'll give you another moment to look at that. And let's move on to our next problem. All right. Which function is continuous at x equals 5? So we're looking for ones where there's no discontinuity at x equals 5. No jumps, no holes, no asymptotes, none of that. Okay? So if you look at A, just from this, it at least appears that there should be a jump discontinuity, right? And in fact, if you kind of start thinking about it, there's all sorts of weird stuff going on. Let's say if you take this and you do, okay, if I factor 2 out to the front and have 2 times the quantity x plus 5 over, I've got a difference of squares on the bottom, so that factors into x plus 5 times x minus 5. So I've got a hole at x equals -5. I've got a vertical asymptote that would be starting at x equals 5. And of course, what we're really doing there, because x doesn't equal -5, is we're taking out the vertical asymptote. We're leaving in the hole because it's that value everywhere except there. And then we've got this one little point filled in for x equals 5, right? And we've just got a y value of -0.2. It doesn't even matter. Well, it does matter that it's x equals 5 because it only happens at x equals 5. So there's all sorts of weird stuff going on there. So that's definitely not continuous at x equals 5. We've got vertical asymptote with like one little point specifically picked out on that vertical asymptote in between as we approach that vertical asymptote. So we'd be doing really weird stuff at x equals 5, right? And then here, again, there's going to be a jump discontinuity, right? Because at x equals 5, as we approach x equals 5 from the left, if you put in 5 there, you'd be hitting 4. And so you would put, so this one I can sketch out a little bit easier than the other one. So if we talk about that being the 5 point, x minus 1 would be, let's say that's 4, let's say that's 5. I'm just giving approximates here. There would be a y value of 4, but we would never hit it, so we'd just put an open circle there, and everything before 5 would look like that x minus 1 line. And you can make a table and sort of confirm that, but that's how it would be. And then at 5 and beyond 5, all the y values are 5. So at an x value of 5, the y values are 5, and then always after that, the y values are 5. Whoops. And there's that. So that's what that one, and clearly there's another jump discontinuity here, right? So clearly, again, something weird going on there that makes it not continuous, is a discontinuity. This one, there's nothing weird going on. I'm not dividing by anything, so I'm not going to get a denominator of 0. This is just a parabola, and if you remember how to read this, this is a parabola shifted in the x direction by 5, by positive 5, and shifted in the y direction by positive 6. So it looks like a regular old parabola, just shifted like that. So it looks like that, and it's certainly continuous at x equals 5. So that one we can say is definitely continuous at x equals 5. And then if you look at the last one, if I put in 5, I'm going to get 0 down here. It's not going to cancel with anything, so that's going to give me a vertical asymptote. So C is definitely my answer here. Okay, I'll give you a moment to think about that. And let's move on to the next problem. All right. We want to complete the sentences to describe this function. All right. So now let's do some work on this function. All right. I'm gonna pull it apart as much as I possibly can, and then I'm going to look at it again. So I could factor out a 2x to the front of the top, and that would leave me with, what would that leave me with? X plus 8, right? And then in the bottom, I could factor out just an x, and that would leave me with, what would that leave me with? 16x squared minus 1. And then, so let me do some stuff to that. First of all, the x's will cancel. So x is canceling there, and that would be 0. So I've got a hole that is a point discontinuity. So I'm going to make some notes here. There's a hole at x equals 0 for sure, right? Because cancellation is happening. So now I'm going to go on with it. So now I've got this, and then this is actually a difference of squares. 4x plus 1, 4x minus 1. And so I could think about how I might get 0 for each one of those. And those would give me 2 vertical asymptotes, right? So that would give me, if I think about 4x plus 1 equaling 0, I would subtract 1 on both sides and have 4x equals negative 1, divide by 4 on both sides, and have x equals negative 1/4. So a vertical asymptote at x equals negative 1/4. And then I can do the same thing with 4x minus 1 equals 0. And for that one, I would add 1 to both sides and have 4x equals 1, divide by 4, and have x equals 1/4. And so there's another vertical asymptote at x equals positive 1/4. So the function is discontinuous at 0, negative 1/4, and positive 1/4. Those are all the different discontinuities that show up. So there's part of it. And then it says to create the extended function. Now, what do they mean by extended function? It's a strange term, and it might be worth looking up. What they mean by extended function. So I think what they mean by extended function is how would we, I guess, continue this? And we're going to take a look at that. So give me just a moment. I'm going to make sure that I am correct in this. I don't want to give you bad information. So give me a moment to make sure about this. One thing that I will tell you, extended functions are not discussed very much in early calculus. So we're going to talk about it, we're going to kind of gloss over it, and we're going to do that because it sort of makes us, but in the actual working out of things, we're not going to worry about it that much. So we'll talk about it, but again, so okay. If I wanted to create what we call the extended function, all I would do is say, where is it discontinuous in its original, whoops, I was trying to circle that. Where is it discontinuous in its original form? And that's at x equals 0. And if we wanted to think about f of x equaling 0, that's where we would go with it. Again, I don't think it's super necessary to talk about, but there it is. Okay, I'll give you a moment to look at that. Well, let's move on to the next question. Which function has a removable discontinuity? Okay, so this is when you factor them and you have a whole. That is, you have something that cancels. So we have to factor each one of these. So in the top here, we've got x minus 8. In the bottom, I want it to factor into two pieces. To get x squared, I need x and x. A minus there means 1's plus, 1's minus. And then I need two things that multiply to make this and do this to make the number attached here, which is 1. And then the bigger number will go with that. So two things that multiply to make 56 are 7 and 8. 8 minus 7 is 1. Bigger number goes with the minus. So 8 and 7. And look right there, we get a removable discontinuity, right? So this one, for sure. And then I've got x plus 3 over x squared plus 1, or x squared plus x minus 1. Can I factor that? Well, I would need two things that multiply to make 1 and subtract to make 1. I don't see that. It certainly wouldn't be x plus 3, so that doesn't even factor very well, so we're just going to not even bother with it. Next one, I've got x plus 7 over x squared minus 49, which you should recognize as a difference of squares. Difference of squares is the square roots added and subtracted. And then we get cancellation, so that's a removable discontinuity. Then I've got x squared minus 36. Well, this is a difference of squares, so it factors into the square roots added times the square root subtracted over x plus 6. The x plus 6 is cancel, so we got a removable discontinuity there. And then there's nothing to factor in this one, so there's no possibility of cancellation here. Remember, you can only cancel between multiplication. Okay? You cannot cancel, like I can't say the 2's cancel because that plus is preventing it. I can only cancel with multiplication. I cannot cancel with addition or subtraction. So no canceling there, no even factoring, no canceling or factoring there. So we've got A, C, and D that wind up being our ones that have cancellation and thus have removable discontinuities. I'll give you a moment to look at that. And let's move on to our next question. Which discontinuity can be seen clearly on any graphing tool? Okay, so these are the ones, again, those removable discontinuities, those holes, those cancellations, you're never going to see those. So holes, removables, no way. Right? Infinite ones, those are your vertical asymptotes. So absolutely. Endpoints. Endpoints are really kind of strange things that, like, for example, if I was creating the graph for f of x equals square root of x, and I'm only concerned about a real graph, it has to actually start at 0, 0, and then it winds up looking like that. So that's an endpoint, and you should be able to see an endpoint pretty well. And jumps, we saw a bunch of jump discontinuities in 10.1, where we had those weird-looking graphs that did stuff like this and then this, where we might have had a graph like that. So jump discontinuities are usually pretty easy to see. So that's, you can see jumps, you can see infinite or asymptotes, and you can see endpoints pretty well. Holes and removables, those are the ones that are tougher to see. All right. I'll give you a moment to look at that, think about that. And let's move on to our final question. All right, so let's consider this function over this interval. And this notation, what this notation means is that we're only concerned with x values from -3 to 4, and the brackets mean that we are including -3 and 4. Another way of putting this would be that x is between and including -3 and 4. So that's another way of describing how we're looking at it. We're just going from -3 to 4 in x values, and we're including -3 and 4. So give the maximum and minimum values. And when we say the maximum and minimum values, we mean the y values. Okay? So when I plug stuff in, what's the smallest number I'm going to get? What's the biggest number I'm going to get? Well, you might sketch this out. You might use a graphing calculator to take a look at this function. I might type in f of x equals x raised to the 3rd power plus 34. And you might just kind of zoom in so that you're looking from -3 to 4 on your graphing tool. Again, Desmos, on Desmos.com is the graphing tool that I would recommend, except for SAT week, where you should probably know how to use a graphing calculator. Although I do have to say, usually there's not a whole lot of graphing this function that means a whole lot on the SAT, the ACT. So you can usually get away with just a scientific calculator and make tables for any graphs that you might need. So, so for the graphing, I recommend Desmos.com for the graphing. And then what you see, and I'll give a quick little sketch here. If this is -3 and this is 4, what we see is that it kind of just does that. There's some curving if you zoom way out, but it goes way up as it reaches 4, and it just goes up the whole time. If I put it on a different scale, if I say that the y's go way up to like 40 or something like that, or 50, then it winds up kind of looking more like this. But the point is, it always goes up, right? So the minimum value should be at an x value of -3. So all I have to do is do f of -3, that is, put in -3 for the x value. And then I'll leave that for you to calculate, but you can see it's fairly easily done, especially with a calculator. And then the max value will be at x equals 4, because those are our constraints, right? That's why our min and max values are going to be at those points, because those are our constraints, as it says right there. Okay. And then I would just figure out f of 4, which would mean 4 cubed plus 34, and whatever that answer is, those are big negative and positive numbers. All right, I'll give you a moment to look at that, and that was our last question for this video, so thank you so much.